In this video clip, I want to give a brief summary of the key topics we've covered in week 2. The intent here is not to go into all the details or hit every single important point, but again to hit the high points, as it were, remind you of some key things, maybe remind you that you perhaps don't understand something quite as well as you thought, or you forgot about something, so you can go back then and look at the video lectures on those topics. So, space-time location of event. We start out, the theme for the week was events, clocks, and observers, and so we talked about how we can specify that event via a coordinate system in 3 dimensions, x, y, and z. X, y, and z in 3 dimensions, and then a time coordinate so that if an event happens, we record its x, y, and z location and its time at that location. Or just x and t. We're going to, for the most part, just deal with things in 1 dimension along the x-axis to make things a little simpler. So we'd specify its location on the x-axis, either in the positive direction or the negative direction, and specify some origin point, and then the time of a certain event as well. That led to some questions, however, and one key question was how to specify the time. How to specify the time. For the x, y, and z coordinates, we assume, of course, we have some measuring system and units of length and so on and so forth. But, and certainly for the time, too, we have clocks, but the question is, if an event happens out there someplace, a flash of light, our classic standard event, and we can specify the x, y, and z coordinates, or just the x coordinate along the x-axis, how do we specify the time? Well, we could say, I've got a nice master clock right next to me here if I'm the observer. I see the flash occur, record the coordinates out there, x, y, and z, and then when I see the flash of light, if it is a flash of light, I record the time on my clock. Of course, there's a delay from when the event occurs and the time the flash gets to me. In most of our real-life situations, the delay is imperceptible, so we don't worry about it. But if we want to be precise, we'd have to take that into account. Now, we certainly can do that so that we could sort of have a little formula for the delay. It's not that difficult, but we'd rather not have to deal with that. So alternatively, what we've imagined is that we have a lattice or a grid of clocks. In other words, we have imaginary clocks at every single point along the x-axis, or in 3 dimensions, every single point in space that we want. And when we want to specify the time of an event, we just look at the clock at that location. So the flash of light, say it occurs right here, and we record the x-coordinate of it, or x, y, z coordinates, and we look at the clock at that instant in time when the flash occurs, the clock right next to it, so there's no delay. We'll get the clock as close as we want to that point, the imaginary clock, and then that will record the time. So we talked about the so-called photo clock principle. And this is just sort of my name for the idea, the photo clock principle. Again, the idea is you have imaginary clocks everywhere. At every single point, there's an imaginary clock. And when an event happens at that point, you record the location. Maybe it's inscribed on the clock, the exact location of it, the x value or the x, y, and z values. And then the clock is running, so you can take a photograph of the clock at that instant in time and read off the time later on when you want to do that. So we say that is what an observation is. It's not an observer here looking off someplace and seeing something happen, as we often use it, but for our precise purposes, an observation means there's a clock at that point where the event occurs. We record the location and the time on that clock, and that is how we observe an event. Okay. Again, these are imaginary clocks, so if we want to measure things to a millionth of a meter, say, we need 1,000,000 clocks every meter. If we need a billionth of a meter precision, then we need 1,000,000,000 clocks in 1 meter, and so on and so forth. Maybe we're only interested in 1/10 of a meter precision, so then we only need 10 clocks per meter, and things that happen in between the clocks then either essentially go to the nearest clock one way or the other. So there is some imprecision there, but it's an imaginary grid or lattice of clocks Therefore, we can imagine as many clocks as we want and as close together as we want. Now, there's still another key thing here we have to think about with our imaginary grid or lattice of clocks, and that is how to synchronize them. And we talked about two basic methods that we could imagine to synchronize our imaginary lattice of clocks. One was, again, to have a master clock. Maybe I'm the primary observer. I have a master clock sitting right next to me. I have all the other clocks. I bring them together. I set them according to the master clock so they're all synchronized. Then I move them out to their various locations. Again, in imaginary fashion. But could do this in real life as well. You couldn't probably have 1 billion clocks a meter that way, but you could certainly have a number of clocks in a lattice and do some actual measurements that way. The problem is, as we will learn a little bit later on here in the course, is once you start moving clocks with respect to each other, they get out of sync. And that was one of the results of Einstein's special theory of relativity. Now, again, it's a question of precision. So if you say, well, I'm only interested in precision to 1/10 of a second, if you move them slowly enough to their positions, they won't get out of sync very much. And the amount they get out of sync is very, very small. But if you want to be very precise about it, that can have an effect. And so, in principle, yes, we could move them out very slowly enough so that there would be slight desynchronization, as it will, as you could say, but not enough to affect whatever measurements we were doing. So that could certainly work. We'd rather avoid that, however, so we talked about a second method. And that second method was essentially have one master clock again, put all the clocks out, say along the x-axis, the clocks that we want in our lattice, but they're not running yet. And then send a signal out from our master clock. Say when the master clock is 12 noon, it sends a signal out in both directions along our line of clocks. And as each clock receives that signal, it starts running. Now, of course, the signal has a slight delay to reach any given clock, and so we'd have to take that into account. And the way we imagine doing that is, let's say the signal takes 5 minutes to reach this clock right here, so it's pretty far away at the speed of light. And so we would say, okay, we're going to put this clock at this position. We know it's going to take like 5 minutes to reach that exactly. And so we'd set this clock at 12:05. And so the master clock sends out the light pulse, light signal at 12 noon. 5 minutes later, it reaches that clock and turns it on. So it's reading 12:05. The master clock is reading 12:05. And so on and so forth for all the other clocks. So that is certainly another way we could synchronize all our clocks, and it avoids this little problem with once you start moving clocks with respect to each other, they get out of sync. So we certainly consider the problem of how to synchronize and talked about those two methods. Then we moved on to space-time diagrams. Space-time diagrams in one dimension only, so we have motion along the x-axis. In fact, let's get a little room here now. Okay, so here is our x-axis, some origin, some tick marks representing however close we want our measurements to be, tens of meters, meters, billions of meters, or whatever. And everything happens along that x-axis. And again, we imagine our lattice, a grid of clocks along that x-axis. And so we could record a series of events. Something happens here, and then here, and then here, and then here, maybe 4 flashes. To represent that in a space-time diagram, we add, of course, a time axis. And then we say, okay, if something happens at time t equals 0, we plot it along here. If it's at position 4, time t equals 0, it'd be right here. Let's put a little dot there. So position 4, x equals 4, time t equals 0, it happens sort of right there. Don't want to mess up my marker too much there. Let's get some more tick marks up here. And of course, if it happens, anything that happens at time t equals 1, assuming it's 1 second, 2 seconds, 3 seconds, 4 seconds, that'd be anywhere along here. So if I have another flash, maybe at position 2, that happens at 1 there, it'd be there. And so on and so forth. So any given event that occurs at a certain x value and a certain time value, I just plot the x value and then the time value. And then we expanded more with the idea of a space-time diagram and talked about world lines. So that if we have an object moving along the x-axis here, constant velocity, we start off with that case, then what we get is a straight line, something like this, at a certain slope or angle there. And this represents the world line of an object. Remember, it's moving along the x-axis through time. So we can see at time t equals 1, it was about in position 1. At time t equals 2, roughly is in position 2. At time t equals 3 is in position maybe 3.25, and so on and so forth. Actually, then it wouldn't be constant velocity motion, but hopefully you get the idea there. Constant velocity, straight line motion like that. We also did some other examples of world lines, just remind you of a few of them. So that was the world line of an object moving to the positive x direction. If you have something moving in the negative direction, it's going to be something like that for constant velocity motion. If you have something that's just like this, a world line like that, that is something that is sitting at x equals 2 as time goes on. Time is going up here, and so this object is just sitting at x equals 2 there. That's a stationary object on this space-time diagram. Another example is something like get curved lines. When you have a curved line, that's something that is accelerating, right? Or decelerating, as the case may be. In this case, we can tell actually it's accelerating because you can see for a given amount of time here, it's traveling a farther distance than it is down here. And so when it bends over, it's accelerating. If it was going something like that, let's not quite do that. That gets to infinite acceleration there, or deceleration, I mean. Let's just do something like that. So this is something that's decelerating. It's actually slowing down. And another reason we can tell that is we talked about velocity. And let's not do the accelerating or decelerating so much here because, as we've mentioned, we're just dealing in this course with constant velocity motion, but it's important to know that a curved line is something where the velocity is essentially changing. It's not a constant velocity. Because we talked about if you have a straight line like this, velocity is just distance covered divided by elapsed time. So distance covered, say if it goes to this point right here maybe, something like that. 1, 2, 3, 4, it's covered 4 units in 3 units of time. Distance covered 4 divided by 3. So it'd be 4/3 meters per second or whatever units we would be using there. So we talked about velocity related to the slope of our world line. And we talked about velocity being the run divided by the rise. So that if we have a world line like that, okay, that's a big run divided by a relatively small rise. That's a high velocity object. It's an object that's moving at a higher velocity. It covers a lot of distance in a relatively short amount of time versus a world line for an object like this, lower velocity. It covers less distance in a bigger amount of time. So we noted that the slope of a line, this is a line with bigger slope than this because slope, remember, is rise over run. Velocity on our diagrams is run over rise, the inverse of the slope. So low slope, smaller slope on our space-time diagrams means something that's going faster versus bigger slope means something that's actually going slower there. So that's how velocity works on our diagrams. And so then, if we let's do a green one here, go back just to the acceleration case very, very briefly. If you have something like this, you can see the slope of this line is gradually bending over, more horizontal. That means it's getting faster over here. It's accelerating. Versus if you have something going the other direction, okay, the slope of the line is getting steeper. Again, on our space-time diagram, that means it is slowing down. It's decelerating. And it's still moving to the right, but it's decelerating as it does that. Remember, once again, I've repeated this a number of times, that this is not the actual motion of the object. It's not shooting off at some angle or curving this way or that way. It's just going along the x-axis. So this green line would be something that started off fast along the x-axis and now is gradually slowing down, still moving in that direction. This one here is an object moving fairly quickly in that direction. This object here is something that's moving relatively slower in that direction. This world line here represents something moving in the negative x direction at a constant velocity. So in our assessment quizzes, we did a lot of examples with world lines. So hopefully you'll, if you haven't already, you'll be working through those, and you'll see more of them on the week 2 review quiz as well, based on the things that you did in the assessment quizzes. Okay, so that was space-time diagrams and world lines. Then from there, so I think we covered everything, again, the main points there. A lot of examples, again, in the assessment quizzes to work on. Okay, let's look at next topic, which was, I think we're up to number 5 now. Frames of reference. Spent several video lectures looking at frames of reference. Did examples with Alice and Bob, and maybe Earth is involved as well. In the assessment quizzes, we introduced Chris into some of our examples. What's the basic idea here? Well, the basic idea goes back to our lattice of clocks idea. And so, in fact, remember, we've had some props here. Here's Alice, say, in her spaceship. This is her lattice of clocks in the x direction. And we can imagine that, as far as she's concerned, she's just sitting there. And she's watching Bob fly by in his spaceship. She can measure his progress by taking photographs as he goes by each of her clocks. There are more clocks here, too, just not shown. So every single point has a clock where she, if she wanted to, take a photograph at that point as Bob flies by or whatever happens at that point. It records the time and the location of Bob, and therefore she can track his progress. But her frame of reference then is her lattice of synchronized clocks. And as far as she's concerned, with respect to her frame of reference, she's just sitting there. She's not going anyplace at all. But of course, Bob, could say, is also in the same situation. You know, he's moving by here like this, but as far as he's concerned, he could be sitting there, and it's Alice who's moving. In this case, she'd be moving backwards. Bob would say, hey, Alice, I'm not moving, you're moving backwards. And Alice would say, I'm not moving, you're moving in that direction, the positive x direction. So Bob also has his frame of reference, which consists of his lattice of clocks, and his frame of reference is, as far as he's concerned, he's at rest. He's got his lattice of clocks. He can measure anything, any space-time event according to his frame of reference. Alice can measure any space-time event with respect to her frame of reference. And in a little bit, we get to the Galilean transformation that allows us to convert between the two different measurements, what Alice might measure versus what Bob might measure in terms of any given space-time event. But before we got to that, we had to make sure the concept was clear of a frame of reference again. It's imagine it just, if these props help or these images help, imagine it as, say for Alice here, just her lattice of clocks, or any observer. It doesn't have to be Alice and Bob in their spaceships. You can say, here I am. I'm an observer. I have my imaginary lattice of clocks. As far as I'm concerned, I'm stationary here, and I measure things going by with respect to that. Somebody else who maybe is traveling by has their own imaginary lattice of clocks, and they can measure things with respect to that. And the observer always stays at the origin of their frame of reference. So, talked about concepts of frame of reference, did some examples with Alice and Bob and world lines as well. We also talked about the concept of an inertial frame of reference. Again, we didn't go too deep into how you'd specify this and some of the technicalities of determining whether you're an inertial frame of reference or not. For our purposes, it's easier maybe to think of a non-inertial frame of reference, and that's one where there's acceleration involved, acceleration or deceleration. So if you're riding a car and you feel that acceleration, the car's acceleration, you push back in your seat. You feel that. If you're going around a corner, that's also a situation with acceleration. You're thrown to one side or the other. If, however, you're traveling along at a constant velocity, assuming you don't feel any wind or anything like that, you're inside a car, then you really don't feel, you're not pushed back in your seat, you're not thrown forward, and therefore, in that direction at least, that's constant velocity, inertial motion. You're in an inertial frame of reference. And the special theory of relativity only deals with inertial frames of reference. So everything we do, we will assume that that's what we're working with here, that we don't have any accelerations involved, at least in the direction that we are considering, usually just the x-axis. We also talked a little bit about combining velocities. Combining velocities, very simply, in, say, non-Einsteinian, in terms, in Galilean terms, in classical physics terms, velocities just add. So if I'm able to throw a baseball or a basketball, tennis ball, whatever, at a certain velocity, say I just have a machine that shoots a ball out. In the video lectures, we did an example with escape pods, Bob having an escape pod on a spaceship, but you can also imagine just a machine that shoots some sort of object out, a ball out, say, and let's say that machine can shoot the ball at 100 kilometers per hour in that direction, and I can measure that. And maybe Bob's standing over there, he measures that coming toward him. If I then get in a car, put the machine on the car, and move at, let's just say 60 kilometers an hour toward Bob, and shoot the ball leaves the machine at 100 kilometers per hour, but the car is also moving at 60 kilometers per hour towards Bob, and so he sees the velocities add, total is 160 kilometers per hour. Or if I have the car going the other direction away from Bob, so it's 100 kilometers per hour going, or 60 kilometers per hour going this way, and the machine is shooting at 100 kilometers per hour, it subtracts. So the effective velocity towards Bob then is 100 minus 60 or 40 kilometers per hour. And of course, if the car is going even faster that way, say 120 kilometers an hour, shoots the ball 100 this way, the ball ends up still going that way, although at only 20 kilometers per hour. Again, the difference between them. So when we're dealing with classical physics before we get to Einstein, combining velocities is very simple. Velocities simply add. Or subtract, depending on the direction of motion there. Even after Einstein, this is true as long as the velocities are low enough, which essentially means most velocities in common everyday life, unless you're working in a physics lab or something like that. So for now, at least, combining velocities is very simple. They just add or subtract. And then finally, we talked about the Galilean transformation. The Galilean transformation. And this is the idea that how do you transform or translate between one frame of reference and another frame of reference if they're moving with respect to each other at constant velocity. Okay? Maybe Alice measures something on her clock, one of her clocks in her position, and if Bob happens to be moving at a constant velocity with respect to her, what would he measure for that event on his clocks and his measuring sticks, as it were, his measuring system? Now, we've actually, when we didn't really derive this, we motivated the equations for this. In fact, let me get a little room here. And we did it with Alice and Bob. In the assessment quiz on one of them, we actually introduced just person 1 and person 2, because it's good not to get too hung up on a certain, Alice is always doing this, Bob is always doing that, because this is one of those things that you can really get confused with plus and minus signs. So let me introduce sort of another way to look at it that can be helpful. The idea here is you memorize one basic situation, and then if you are sure about that, you can usually very easily apply it to a second situation. So we're going to have two frames of reference here, and we're going to label them the lab frame. So this actually isn't officially, it's a summary of what we've done, but slightly different terminology here, so we're introducing something a little new. And we're going to talk about the rocket frame. Two frames, lab and rocket frame. So the advantage of this is versus, say, Alice and Bob, you say, okay, in general usage, the lab is stationary, the rocket is what's moving here. And so here's our rocket going by with some velocity v, and we're going to assume that the rocket is going to the right. So that's going to be our standard situation. Lab frame observing a rocket or whatever object it is moving to the right there. And of course, if this is Bob or Alice, whoever, in the rocket frame, the rocket has its own frame of reference. Okay, so as far as this is concerned, whoever is in the rocket is stationary, has their imaginary clocks going in both directions there, and they could measure any event on their clocks. But the question is, if they measure something on their clocks, what is the measurement going to be? What are the coordinates going to be in the lab frame? And again, without going into sort of how we semi-derived it, let's just write down the basic equation here. Is assuming something has been measured, again, let's say it's Bob here. He's going along here, and he sees an event out here someplace, and he records it on his clock there. The question is, what is that on? Let's say Alice is in the lab here. So Alice is stationary, watching Bob goes by. Bob records something way out there. The question is, what is the location and time on Alice's clock? So it'd be, Alice's clock, something like that at that instant of time. So here is the basic equation in lab and rocket terms. X lab equals X rocket. Okay, and then here's the key thing. Is it plus or is it minus? Okay, because essentially we know the distance between the rocket and the lab in terms of the origin, and we always assume that at t equals 0, should have mentioned this, reminded you of it, at t equals 0 their origins were the same, so they're right next to each other. And then at a later time, the rocket goes in that direction to the right. That's what we're assuming. So note that the lab position here is going to be greater. Okay, so we're imagining it was right out there, that last clock, say, on our prop here. And clearly, if the rocket is moving in that direction and measures something way out there at this instant of time, then for the lab frame, it's going to be at a greater position, a greater x location than in this frame. And so it's a plus sign. So it goes plus vt, where the velocity times the time elapsed is just how far the rocket has moved in that given amount of time. So at time t equals 0, they're right here. And if Bob, at that instant in time, saw something here, if I can get this, saw something right there, then Alice would see it at the same clock and position. But a little bit later, velocity times time, Bob has moved a certain distance, and therefore, if it's the same clock, it's that clock distance plus the time he's moved, or the distance he's moved. Velocity times time. So this is the basic equation. X lab equals X rocket plus VT. So again, lab frame, rocket moving to the right. They start at t equals 0 right next to each other. The rocket's coming by, and then right at t equals 0, it passes by the origin there, and then continues on that direction. So the lab value here for the location of whatever event occurs that's been measured in the rocket frame is going to be greater by VT than what it is in the rocket frame, because the rocket is going off there to the right in the positive x direction. So if you remember this basic situation, say, okay, lab frame, a rocket moving to the right, here's the Galilean transformation. If I measure something in the rocket frame and I need to find out what it is, what the location is in the lab frame, the stationary frame in our example, you just add VT to it. And then given that, you can say, okay, what about other situations? Well, what if the rocket was moving the other direction, to the left? You just change the sign here. It just becomes minus VT. And then you can say, that's really the same thing. So you can say X lab equals X rocket minus VT. Okay, so this is motion to right. And this is motion to the left, negative direction. And then you say, well, what about the rocket itself? Remember, the person on the rocket, they have their own frame of reference. With respect to them, the lab is moving to the left, right? They're moving to the right, but if they're motionless, everything else is moving to the left. And therefore, you use the left equation, the left motion equation. So we have a left motion equation and a right motion equation. And you just have to say, okay, if we're really talking about the rocket, the person in the rocket, the observer in the rocket, then they are the lab now. And whatever they're watching outside of them is the rocket or the moving object. So we could say the stationary observer and the moving object, if you want to look at it that way. But again, I'd recommend to sort of get one situation visualized in your mind and know how it works, and then you should be able to figure out the other situations depending on whether you're moving left or right, and it's just a difference in minus sign there. And again, it's very easy to mix it up and get the wrong minus sign there. So it does usually require, until you've done this a lot, requires a little bit of thinking. Make sure you understand the situation, which way the motion is, who is the stationary observer. Could be either the rocket person or the person in the lab. It just depends whose frame of reference we're talking about. And then the correct equation based on either motion to the right or motion to the left. So that's maybe a little bit longer summary than anticipated here, but I did want to go into a few of those details. And it gives you a nice overview of the things we've done in week 2. And then as we move into week 3, where we talk about things like waves and the Michelson-Morley experiment and stellar aberration and Einstein's 2 key principles or postulates that were the foundation for his special theory of relativity. So all that is coming up.